I'm going to go over a common CodeSignal question 4, which is to do with lamps or streetlights. It's a pretty common CodeSignal question 4, but kind of notoriously difficult because it's not like the typical just hash map solution that most question 4s are. And it's really easy to get TLE on. It's got pretty tough time constraints usually, and the approach that most people would use, even though it's probably correct, will get time limit exceeded, which is the issue people have with this question, which is what makes it a bit difficult. The approach I'm going to use to solving this is a line sweep algorithm. So I should note that there's actually multiple variants of this like lamp question on CodeSignal, so they can tweak some like variables, like maybe instead of having multiple of some things, it'll only be one, or they'll ask you for different things, so small changes basically. And for some of them, it may make it so this isn't the right algorithm to use, but this is still, I think, good to know if you're ever going to take the CodeSignal test. So as for what the question actually is, basically you're given a really long coordinate line, so like you can see here, and you're given a certain number of lamps along the line. So in our case, we have 4 lamps along the line, and for each lamp, it's going to give you a range that lamp is illuminating. So for example, our very first lamp is illuminating from -20 to -3, which you can see here, from -20 to -3. Our second lamp is from -10 to -1, and so these are inclusive ranges. So this lamp is illuminating the coordinate -10, and it's illuminating the coordinate -1, so it's inclusive. So on top of being given those lamps, you're also going to be given a series of benches. So in this case, I represented the benches as just red circles, and it'll tell you where all those benches are along the coordinate line. So for example, our first bench is at -17, our second's at -10, and so on. And so what the question is you need to find how many lamps are illuminating each bench, and then you're going to return that as like an array. So for example, our first index in the array is going to be how many lamps are illuminating our first bench. The second index is going to be how many lamps are illuminating the second bench, and so on. So from the picture, it's pretty easy to see the answer. So for example, we can run through and figure it out. So for our very first bench, there's only one lamp illuminating it, right? Our very first lamp. So that would be our very first index in our answer array. For our second bench, there's actually 2 lamps illuminating it. It's right on the corner of this second lamp's range, but since it's inclusive, it does count. So our second bench has 2 lamps illuminating it. Our third bench has 3, so it's got this first, second, and third lamp all illuminating it. Our fourth bench only has 1. Our fifth bench has 2 lamps illuminating it, and then our very last bench actually doesn't have any lamps illuminating it. So that's why we would get 0 for that. So the algorithm itself, or finding the answer isn't too difficult. Like you can see it once you have this picture, obviously. But given the time constraints and the fact that there could be tons of lamps, tons of benches, and spaced out over a very large coordinate line is what makes the question difficult. So to give like a formal description of the problem, they're going to say there's some sort of infinitely long coordinate line. So in practice, it's going to be just with a really large upper bound, maybe like 10 to the 9th power or something like that. And you're going to have some number of lamps along that line. Then you're going to be given those lamps as a 2D array of integers. So lamp sub I is basically the range of coordinates that the ith lamp is illuminating, like what we saw in the previous picture. And yeah, we mentioned that was inclusive. And then you're also given those benches, which is going to be just another array of integers. Basically, it tells you what coordinate is this bench on. So the benches sub j is going to be the coordinate of the jth bench. And so our task is to find how many lamps are illuminating each of those benches along this line. So basically, we're going to be returning some integer array where each index is just the number of lamps illuminating that index's bench, more or less. So as for how you can actually approach this, we mentioned we're going to be doing a line sweep algorithm. So all that really is, it's pretty intuitive, is we're just going to move over the timeline from left to right, and we're just going to keep track of the number of lamps that are illuminating the current point, just like the current coordinate. So when you see this, you may think we're going to run through, every single coordinate. So we're going to start, -20, -19, -18, so on and so on and so on, until we've covered all of the values essentially. But that isn't feasible because, like we mentioned, it was a really long coordinate line. So you could have, tons of coordinates to look through. So you can't realistically do that. So instead, what we're going to do is we only want to consider points along the line that are actually relevant to our problem. So we only want to consider points along the line that have either a lamp illuminating them or that they have a bench on them, basically. And so the way to do that is to consider basically 3 just events. So we're going to break up this whole problem into 3 events. And those 3 events are if a lamp starts illuminating, if a lamp stops illuminating, and if we encounter a bench. And so the whole idea is that if a lamp starts illuminating, we're going to increase some counter for how many lamps are currently illuminating. So that makes sense, right? If we're running left to right, anytime that we see a lamp start illuminating, we'll increase a count for how many lamps are illuminating. If we see a lamp stop illuminating, then we're going to decrease that counter. And then the third type of event is if we come across a bench. And in that case, all we have to do is just take note of how many lamps were currently illuminating when we came across the bench. So these are the only 3 events that we care about. So the only trick that we need to be careful of is what happens if the events happen at the same time. So like, how do we break the tie between these events? And the thing is, we have to process them in a very specific order, and that order is going to be from the lamp starting to illuminate is our first event. Then if we encounter a bench, that should be the second event we process, and then the third event should be if we stop illuminating. And so the reason we do it in that order, if we imagine this example, let's say we come to time, or the coordinate here at -10, which is a case where we have multiple events. So at -10, we see not only do we encounter a bench, which is one type of event, but we also come across a lamp starting to illuminate event. So there are 2 events happening at coordinate 10, but it's important that we process the lamps starting to illuminate first, because that way the count for how many lamps are illuminating when we process the bench event is going to be the correct number. If we were to process the bench event first before we accounted for this lamp, then this bench would think it's being illuminated by 1 less lamp than it really is. So that's sort of why that ordering is important for this problem. So really the idea behind how we're actually going to do this is we're going to use a priority queue for events, where we mentioned we have those 3 events, right? Starting to illuminate, if a lamp stops to illuminate like you see here, or if we come across the bench. And we're just going to put them into this priority queue with a specific ordering, and then we're going to go through and process all of those events. So the ordering is primarily going to be based off of time, right? So we want orders, or time or coordinates, however you want to interpret the problem. So we want to put events into our priority queue based off of the time they occur primarily, and then we're going to break ties based off of the type of event it is. So we'll run through an example of sort of creating that event priority queue, so you can see sort of how it works. So to start, let's look through our events. So the very first event, we're going to process our lamps first, and we're going to come up with all the lamp events that we can, and then later on we'll move on to the benches. So if we consider all of our lamps, and we'll process them in this order from left to right, sort of the way that they're given to us, our very first lamp that we come across, we see has a range from -20 to -3. So what that tells us is at -20, there's a lamp start illuminating event, and at -3, there's a lamp stop illuminating event. So we'll go ahead and put those into our priority queue. So we have a lamp on at -20, and we have a lamp off at -3. And then we'll move on, and we'll start considering our next lamp. So our next lamp we see is from -10 to -1. So if we put that into our priority queue, notice the priority queue is sorting based off of the time, right? So it's going to automatically keep all the events in order for us, which is why it's so useful. So we added our lamp on at -10, which we saw got inserted here, and then our lamp off at -1 over here. And then we'll keep doing that, so we'll process our next lamp, and so we see a lamp on event at -5 and a lamp off at 14. So we expect that to update accordingly, and it does. We see our lamp on was inserted in here, and we had our lamp off at the end. We'll do that again for our last lamp, so lamp on at time 11, so we would expect a lamp on event to sort of insert itself here, and a lamp off event at 15, so we expect that to be here in our priority queue. Okay, and that's exactly how it does. So we've processed all of our lamp events, essentially, so all of our lamp on and lamp off events, but we still need to process all these bench events, right, the third type of event that we have. So we'll go through and do that now. We're going to process all the benches. So to start, we'll process our first bench, whatever the first bench they happen to give us is. In this case, it's a bench at -17. So we're going to put a bench event into our priority queue, and it happens to be at -17, so it gets inserted over here. We'll move on to our next event at -10. And so here's actually an interesting case, because we mentioned this is where there's sort of those overlapping events, so 2 events are happening at the same time. So what order should we put our bench on, or our bench event? Should we put it before the lamp on at -10 or after? And so like we mentioned before, we have to make sure we put it after the lamp on event, because that way it will account for this lamp that is actually illuminating it. So we would expect our bench event at -10 to appear just like that up here. And it does, so it appears after our lamp on event. So we just need to make sure, essentially, when we're constructing this priority queue, that we keep that ordering in mind. So the first order is based off of just the coordinate value, and then the second is based off of what type of event it is. So that way they're all in the correct order. And then we'll move on, we'll process our next bench, which is at -4, which gets put in here, then our other bench, which is at +4, which gets put in here in the event queue. but then we have benches at 12 and 16. So bench 12 and bench 16 are all put into the event queue. So now that we have all these events, we can actually run through our, our queue of events and process them in a way that will tell us exactly how many lamps we're illuminating each of these benches. And so hopefully you can kind of see sort of the intuition behind how we're going to do that. We run through, if we see a lamp on, we're just going to count, increase our count for how many lamps are currently illuminating. If we see a bench, then we're just going to mark down how many lamps we're illuminating at that point, and then we're just going to keep that process. If we ever see a lamp off, we'll decrement the number of lamps illuminating. So we'll run through and do that sort of example. So we start with lamp on at -20, right? So that turns the lamp on, that increases the number of lamps that are currently illuminating from 0 to 1. So we have 1 lamp illuminating, and we process that event. Then we see a bench at -17, so that's our next event that is going to happen from the priority queue. And so we see, whenever we see a bench event, we just need to mark how many lamps we're illuminating at that point. So we're going to process the bench event. We know that there was 1 lamp illuminating, and so that's what we're going to put into our answer. We'll continue. We see a lamp on at -10, so that's going to increase our number of lamps illuminating up to 2, and we process that event. We see another bench as our next event, so we're going to mark down 2 because that's the number of lamps we currently have illuminating into our solution, and so we process that bench. We see another lamp on event is our next one, so that's going to increase how many lamps we have currently illuminating to 3, and then we process that. We come across another bench, so we'll mark that down into our answers. There were 3 lamps illuminating when we came across this bench. We'll go ahead and process that. Now we see a lamp off event, so all that does is actually decrement the number of lamps currently illuminating. So one of the lamps turned off, so now there's 1 less turned on, and we'll go ahead and process that. We see there's another lamp off event, so that decrements the number of lamps yet again back to 1. I'll go ahead and process that. We come across another bench, so for this bench there's only one lamp illuminating at this point, so we'll put that into our answer array, and that bench is now processed. We see another lamp on event, so we'll increase how many lamps are illuminating back up to 2 and process that event. We come across another bench event, so for the bench event we see, okay, we had 2 lamps illuminating, we'll put that into our answer down here, and then we can process that. We have a lamp off event as our next one, so that will decrease how many lamps we have turned on back to 1, and process that event. We have yet another lamp off event, so that decreases how many lamps we have turned on to 0, and we process that. And then we have our final event, which is a bench event, and we see that when we encountered this bench there were 0 lamps turned on, so that's going to be our final index in the array there, and then we've processed that final event. And so that's sort of how the slide sweep algorithm works. The main thing to notice is that we're not running through all of the possible timelines. So at no point did we iterate over, if we go back, if we go way back, at no point did we iterate from -20 all the way up to 16, because that wouldn't be feasible. Because imagine if instead of -20 to 16, what if it were -10 million to +10 million, right? Instead, all we iterated over were these coordinates up here, and then the coordinates of the benches. So that's what makes this approach sort of feasible in the first place. Okay, so now I'm going to run through an actual coding example for this algorithm in Java. So I set up some boilerplate code, just for starters, the exact example that we just ran through with the same lamps and benches. And I'm just outputting a result here. Down here is where we're actually going to implement the algorithm. So like we mentioned, we're taking in just the lamps and the benches. That's all the parameters, and then we're just going to return that integer array that we mentioned. So to start, we mentioned we have this priority queue of events. So we basically need a way to represent events, so the 3 types of events, so a lamp arriving, or a lamp turning on, a lamp turning off, and then encountering a bench. So I think the easiest way to actually represent those is just with an integer array. So basically we're going to have our integer array where the first thing in our array is going to be the type of the event, and then the second thing is going to be the time of the event, so when does that event occur. And so those are the only 2 things we're really interested in for any event. So for example, we encountered a bench at time, or at coordinate 4. So that's how we'll represent it. So since this is an integer array, we need some mapping between integers and the type of the events. So that's pretty simple. We can just say that, okay, 0 is a lamp turning on. We can say that 1 is encountering a bench, and that 2 is a lamp turning off. So that way, if we see 0, 3, we know that that was a lamp turning on at time, or at coordinate 3. Okay, so with that we can make our priority queue. So our priority queue is going to be one of integer arrays, and this is storing our events. So this is going to be a new priority queue. And so in this priority queue, the important thing really is the ordering. We need to make sure that we're adding events in an order based off of, for starters, their time, or the coordinates. We want earlier events first, and if there are any ties, we have to resolve those based off of the type of the event. So just to be super explicit, I'll do that with a comparator. And so we're going to be comparing two events. So we're going to be comparing event 1 with some event 2. And so when we're doing this comparison, we mentioned the first thing we're interested in is the time. So if the time of one event, which is, I'm using index 1 because we're saying that that's the time. So if the time of one event is different from the time of another, it's not equal to the time of another event, then in that case we can simply return whatever the time is. So if their times are different, then we just use the time as the comparison, essentially, is what's going on here. So if the times are different, we compare them based off of their time. If the times are not different, then we need to compare them based off of their type. So in that case, we're going to do the comparison based off of the type, like so. So comparing them off of the type. And so you notice I put the types in an order such that it's like the order that we want to encounter them. So we first process lamps turning on before we process encountering a bench, before we process lamps turning off. So that's why this ordering is kind of important for the way I have the comparator set up. Okay, so that's our priority queue. That's going to handle storing all of our events. Now we have to actually populate it. So we need to add events to our priority queue. So to do that, let's start by adding all of the lamps. So we'll go through, basically for every lamp in our lamps array, we need to add the lamp turning on and then the lamp turning off event. So, because every lamp has an event where it turns on and an event where it turns off. So we'll add that to our events. We'll represent events as an integer array. So this will be our lamp turning on. And so what is the type in an event of a lamp turning on? We said it's a 0, so that's going to be our first element. And then the second event is when that event actually occurs, and we get that from our lamps array. So our lamp sub 0, that's when the lamp turns on. And then similarly, now let's do a lamp turning off. So lamps turning off, that's an event of type 2, and that is held in the first index. So that'll add all of our lamp events. The priority queue will sort them as we expect in the correct order for the algorithm. The other thing to add is going to be the benches, so any encountering a bench event. So we can go through and do that. We'll loop through all of our benches. And for every bench, we have to add whenever we encounter it into our events. So if we encounter a bench, we said that's an event of type 1, and we need to put whenever that event happened, or the coordinate of that event happening, which is just held in our benches array. So that's benches sub I. So this adds our lamp events. This will add all of our bench events. Now we just need to go ahead and process all the events. So process events. And so the important thing when we're processing events is that we need to track the number of lamps illuminating at the current point, and we need to store that value for each bench. So we're going to run through all the events, process them, update this counter, and then if we come across a bench, we just store the value, just like we did in the example before. So to start, we need some way to store the value. So that's going to be our answer. That's what we're actually returning is with this algorithm. And so that's going to be an array of the same size as our benches, because there's one entry for every bench, right? So we need to track how many lamps are turned on for each bench. And then we have that counter. So that would be our number of lamps illuminating. And that is initially 0. Initially there's no lamps turned on. Okay, now we just have to iterate through as long as there are some events. So our events is not empty. We're going to keep looping. And essentially we just need to process an event every time. So let's get that event off of our queue. So we'll get the next event, which is an integer array, right? So this is going to be the next event from our event queue. And then based off this event, all we're concerned about is what type of event was it. So we need to know, was it a lamp turning on? Did we find a bench, or did a lamp just turn off? So if our event is of type 0, and so a lamp event of type 0, that means that a lamp turned on. So if the lamp turned on, then we need to increase how many lamps are illuminating. That makes sense. What else can happen? So let's say our event is a lamp turning off. So if it's a lamp turning off, that's an event of type 2, like we set up here. So this would be a lamp turning off. And in that case, we just have to decrement how many lamps are currently illuminating. And then the third type of event that can happen is if we come across a bench. So if we come across a bench, we need to store that answer, right? We need to store how many lamps are illuminating at this point in time, which we're going to put into our answer array. And so you need to store how many lamps are illuminating. So kind of tricky thing about this, we need to make sure we get the index right. We need to make sure that whatever we're putting in our answer array, you know, the ith answer needs to correspond to the ith bench. And we don't actually have any sort of reference to that, whatever I is in this case. So one idea might be, okay, let's just track an index, right? So we're going to start off by putting in the answer for our first bench, you know, the 0th index, and then the second bench, the third bench, and so on. So that might look something like this, where we put in, you know, whatever our bench is, and we're just going to increment it to move on to the next bench. And so this might look okay, but it does actually run into an issue if our benches aren't sorted in this order. So let's say, for example, that we actually had our benches given to us in this way. So they're still the same benches, but they're given in an order. They're given in a slightly different order, so not sorted order. And that would actually throw this answer off because it no longer maps like our index directly to the event that we're getting, right? Because we're expecting, you know, we're actually going to get the event for our -17 because it happens in a lower coordinate before we get this event. So that's gonna mess with our answer there. So an easier or sort of workaround to this is instead of having, you know, this index down here, and I'll also fix this before I forget. Or well, I suppose it doesn't matter actually. So every single time that we come across a bench event, we need to also track essentially where that bench was. So on top of tracking for a bench event the type of the event and the time of the event, let's say that we're tracking the type of the event, which in this case is a bench, the time of the event, and then the location or like coordinate bench. And so that way, anytime we create an event, we also tag in to this integer array where that bench was. So in this case, it's just I. So whatever bench we happen to be currently coming across, we're going to put that into its event. And then down here, anytime that we're processing an event, we can very easily get whatever index or location or coordinate that bench was at. And that's just going to be stored in the 0, 1, 2, in the second index, right, in the array. So we can go ahead and get that from our event sub 2. And so that's going to be getting us the correct bench. And so that will populate our answers, and that's just what we have to return as the answer to our question. So if we run this, hopefully, 213120 as the answer. And so why are we getting 213120, which is slightly different from what we got in the example? It's because we switched these two right here, right? So the bench at coordinate -10 now corresponds to the first index, whereas the bench at coordinate -17 corresponds to the second index over here. So that's sort of why, like if we switch these back, for example, back to -17, back to -10, and run it, we get the exact same as what we got when we ran through the solution. And so that's because we tag in the coordinate of the bench into our event. And so just to prove that the other case with using the index would fail, if we switch this back and we just track our index down here. So obviously this will work for this case because they're, you know, in this order we expect. But let's say we switch these and then run it again, we get the exact same ordering. So, and that's because we're not really tracking the index directly to the bench, right? So in this case, the bench is switched and it's not reporting them correctly. It's sort of tracking them based off the benches that come out of the priority queue rather than the way they're actually stored in the array, which is what we care about. So that's why you should go ahead and tack it on to whenever we create an event. And so that's sort of the line sweep algorithm in Java. It's pretty straightforward. And just to consider consider the time complexity real quick. So the time complexity is going to be O of n log n, and that's basically because we're adding all these events once into this priority queue. And then the space complexity is just going to be O of n because that's going to be the size our priority queue can possibly reach.